Welcome to Lecture 11. This week I'm going to talk about antiderivatives, integration, and the definite integral. First, let's cover Chapter 30, which is about antiderivatives. What is an antiderivative? Think of this as doing the opposite of doing differentiation. Capital F is an antiderivative of small f on an interval I if the derivative of capital F is equal to small f for all x in the interval. So, for example, we know that 2x is the derivative of x squared. Change these around and do it in the opposite direction. X squared is an antiderivative of 2x. Or another example, sine x is an antiderivative of cos x, because if we differentiate sine x, we get cos x. And we can we can add antiderivatives together. If we're starting with the function 2x plus cos x, we know that x squared is an antiderivative of 2x. We know that sine x is an antiderivative of cos x. Add them together. X squared plus sine x is an antiderivative of 2x plus cos x. Now, before we go on, let me point out that x squared is not the only derivative of 2x. We can add on a number and we still have an antiderivative. For example, x squared plus 1 is an antiderivative of 2x because if we differentiate x squared plus 1, we get 2x. X squared plus 5 is an antiderivative of 2x because if we differentiate x squared plus 5, we get 2x. And we could put any number here. X squared minus 1,234 is an antiderivative of 2x because the derivative of x squared minus 2x is x squared minus 1,234 is 2x. So let's write this idea as a theorem. If capital F is an antiderivative of small f on an interval I, then the general antiderivative, that's the formula for all of the antiderivatives of small f, is capital F plus c, where c is a constant. For example, find an antiderivative of small f of x is equal to 3x squared that satisfies f of 1 is equal to minus 1. Now we've got to do two things here. We need to find first the general antiderivative of 3x squared, and then after that we need to choose the correct antiderivative which satisfies the second rule that f of 1 is equal to minus 1. So first of all, we need the general antiderivative of 3x squared. We know that x cubed is an antiderivative of 3x squared because if we differentiate x cubed, we get 3x squared. Add on c and we get the general antiderivative of small f. So that's the first part done. We've got the general antiderivative. For the second part, we need to choose the correct value of c so that we get f of capital F of 1 is equal to minus 1. So this is what I'm going to start with. I want capital F of 1 is equal to minus 1, so I'm going to start just here. But we know that capital F is x cubed plus c, and if x is 1, that's 1 cubed plus c, or 1 plus c. But if 1 plus c is equal to minus 1, then c must be minus 2. So the answer to this question is x cubed minus 2. Let me say that again. We know that the general antiderivative of x is x cubed plus c, and now we found that c must be minus 2. So the antiderivative which satisfies both of the conditions in the question is x cubed minus 2. Let's just recap some common derivatives that we've been talking about. I can cross the bottom line out of this in this table out. Recall that the derivative of x to the power n is n x to the power n minus 1. We decrease the power of x and we multiply it by n. The derivative of sine kx is k cos kx, and the derivative of cos kx is minus k sine kx. Doing the antiderivative means going backwards. So how do we go backwards? Well, the opposite of decreasing the power is increasing the power. So we increase from x to the power n to x to the power n plus 1. The opposite of multiplying by a number is dividing by a number. So we need to divide by something. And what do we divide by? We're going to divide by n plus 1. And then every time we're doing general antiderivative, it's always going to be plus c. To convince yourself that this is true, take x to the power n plus 1 divided by n plus 1 plus c and differentiate it. And what do you get? You will find that when you differentiate this, you get x to the power n. Now, let's go down to the second row. What is an antiderivative of sine kx? Well, we know if we differentiate cos kx, we get minus k sine kx. So going backwards, we would go from sine to minus cos. And instead of multiplying by k, we're going to be dividing by k. General antiderivative of sine kx is minus 1 over k cos kx plus c. We also know that if we differentiate sine, we get cos. So do the opposite. An antiderivative of cos is sine. And instead of multiplying by k, the opposite is dividing by k. So the general antiderivative of cos kx is going to be 1 over k sine kx plus c. Just as for derivatives, we have a sum rule and a constant multiple rule for antiderivatives. Suppose that capital F is an antiderivative of small f. Suppose that capital G is an antiderivative of small g, and suppose that k is a number. We have the sum rule. If we can just add the antiderivatives together. Note we only need one c. We're going to do capital F plus capital G, and then at the end we're going to put on c so that we get the general antiderivative. And constant multiple rule. If small f is multiplied by k, then capital F is going to be multiplied by k as well. For example, find the general antiderivative of 3 over the square root of x plus sine 2x. Our f is of the form 3g plus h, where g is x to the power minus a half and h is sine 2x. We're going to find an antiderivative of small g, an antiderivative of small h, and then we're going to do 3 capital G plus capital H. How do we find an antiderivative of small g? Well, this is x to the power n. We increase the power by 1, and then we're going to divide by the new number. So divide by minus a half plus 1. That's the same as x to the power of a half divided by a half, or 2 root x. What is an antiderivative of sine 2x? We've seen this. Minus a half cos 2x, because if we differentiate minus a half cos 2x, we get sine 2x. And therefore, the answer to this question is going to be 3 times capital G plus capital H. So that's 6 root x minus a half cos 2x, and then at the end we do plus c. We have another name for the general antiderivative of a function. It's also called the indefinite integral of f with respect to x, and it's written like this. This large or stretched letter s is called the integral sign. The function that we're trying to find the general antiderivative of, or find the indefinite integral of, is called the integrand. And the dx on the end tells us that x is the variable of integration. For example, the integral of 2x dx is x squared plus c. The integral of cos x dx is sin x plus c, and the integral of 2x plus cos x dx, sum rule, x squared plus sin x plus c. For example, calculate the integral of x squared minus 2x plus 5. And I'm going to solve this problem in 2 different ways. Let's suppose we can immediately see an antiderivative of x squared minus 2x plus 5. Let's say straight away we can see that the derivative of x cubed over 3 minus x squared plus 5x is our integrand. Then immediately we can write down that the answer is this function, x cubed over 3 minus x squared plus 5x, and then at the end plus c to get the general antiderivative. Or we could use the sum rule to split this up into 3 easier integrals. Instead of integrating our whole function, we could integrate x squared, and then minus, integrate 2x, and then plus integral of 5. An antiderivative of x squared is x cubed plus 3. That means the general antiderivative of x squared is x cubed plus 3 plus a constant. The general antiderivative of 2x is x squared plus a constant. And the general antiderivative of 5 is 5x plus c plus a constant. But the key thing to remember here is we only need one constant when we do a general antiderivative, or when we do an indefinite integral. Instead of a c1, a c2, and a c3 here, we just need one c. So we can replace c1 minus 2, c2 plus c3 by just plus c. And then we get the same answer that we got in solution 1. For example, you drop a box off the top of a tall building. The acceleration due to gravity is 9.8 meters per second squared. You can ignore air resistance. How far does the box fall in 5 seconds? Here's a picture. This is you at the top. And you're dropping a box off the edge of this building, and the box is going to fall straight down, and it's going to accelerate due to gravity. The distance the box has fallen we're going to call s of t, and the velocity of the box we're going to call v. The question tells us that the acceleration is 9.8 meters per second squared. But if we differentiate velocity, we get acceleration. Or to say it another way, velocity is an antiderivative of acceleration. So we're going to take the general antiderivative 9.8 to get the velocity is 9.8t plus c. What can we say about c? Well, you let go of the box at time 0. That means at time 0, the box has 0 velocity. But if v of 0 is 0, then we must have that c is equal to 0. So the velocity at time t is 9.8 t meters per second. Moving on, velocity means the derivative of position, or the derivative of the distance fallen. So saying that another way, the distance fallen is an antiderivative of the velocity. So we can take our formula for the velocity, find and then write down the antiderivative. The distance fallen is going to be 4.9 t squared plus a constant meters. What do we know about the constant? Well, again, you let go of the box at time 0. So in 0 seconds, the box has fallen 0 meters. S of 0 must be 0, and therefore the constant must be 0. This means that the distance fallen is 4.9 t squared meters. The question said, how far has the box fallen after 5 seconds? We have our formula for S of t, so we can calculate S of 5, and we find that that is 122.5 meters. Let's move on to chapter 31, which is about integration. What is the area of this region R? It's the area between the graph of y is equal to 1 minus x squared, the x-axis and the y-axis for x and y greater than or equal to 0. Well, we could approximate this using 2 rectangles. There are 2 rectangles here. This is rectangle 1, and then for rectangle 2, I have this rectangle of height 0. We know how to calculate the area of a rectangle. Both rectangles have width a half. The right-hand rectangle has height 0, and the left-hand rectangle has height 3/4. How do I know that? Well, because this is y equal to 1 minus x squared. If x is a half, that's 1 minus half squared. 1 minus a quarter, that's 3/4. We can say that the area of the region R that we want is approximately equal to the area of 2 rectangles. The area of the left rectangle is its height, 3/4, multiplied by its width, a half, and the area of the right-hand rectangle is its height, 0, multiplied by its width, a half. We get 3/8. Can we do better than this? The answer is yes. We could use more rectangles. We could use 4 rectangles. And then we could say the area of R is approximately equal to the area of 4 rectangles. And I'll leave it for you to check that if we do that, we find that the area of R is approximately 0.53125. Can we do better again? Yes, we could increase the number of rectangles. And each time we increase the number of rectangles, the total area of the rectangles is going to get closer and closer to the area of R. For example, if I use 16 rectangles, and if I do this calculation, I find that the area of R is approximately 0.63476. Now, we've talked about limits a few weeks ago. We know what to do if we want to say increasing, if something gets closer and closer as another quantity changes. What we're going to do is we're going to write down a formula for the area of n rectangles, and then we're going to take the limit as n tends to infinity. So this is what we're going to do. We're going to start with the interval from 0 to 1, and we're going to cut it into n pieces, and each piece will have width 1 over n. And then on each one of these pieces, we're going to draw a rectangle. We're going to be using n rectangles to approximate the area of R. And then we're going to take the limit as n tends to infinity. Now, because we're using the right-hand edge of each rectangle, the right-hand edge of each interval to determine the height of the rectangle, that means the first rectangle has width 1 over n and height f of 1 over n. The second rectangle has width 1 over n. The widths are always 1 over n, but the height of the second rectangle is f of 2 over n. The height of the third rectangle is f of 3 over n, and so on. So if we add the areas of all of these n rectangles together, using sigma notation that we talked about right at the start of the term, the area of these n rectangles will be the sum of the area of the kth rectangle. That's the sum from 1 to n of 1 over n f of k over n. And remember, our function is equal to 1 minus x squared. So instead of f of k over n, we can have 1 minus k over n squared. We can simplify this a little bit, and I'll leave some of these details for you to check. We can write this as the sum from 1 to n of 1 over n. That's the sum of a constant number, 1 over n plus 1 over n plus 1 over n plus 1 over n, etc. N lots of 1 over n. And then minus the sum from 1 to n of k squared over n cubed. N is a constant here, so we can take that outside the sum and just have 1 over n cubed, sum of k squared. Back in part 1 of this course, we had a formula for the sum of k squared. If you look back to one of the early chapters, you'll see that the sum of the first square numbers is n plus 1, 2n plus 1 divided by 6. So we end up with our formula 1 minus 2n squared plus 3n plus 1 divided by 6n squared. This n cancels with one of these. We end up with just n squared on the bottom. That's why it's 6n squared on the bottom. N plus 1 multiplied by 2n plus 1 gives us 2n squared plus 3n plus 1. Okay, so now we have a formula for the area of n rectangles, and then we want to take its limit. And I'm going to skip some details here. When we take the limit of this thing as n tends to infinity, we get the answer 2/3. That means the area of the region R is 2/3. Let's make this a little bit more general. Let's suppose we're trying to find the integral of some function y is equal to fx. Let's say we're trying to find the area between this function and the x-axis, between a and b. And we're going to use the idea that area above the x-axis is positive and area below the x-axis is negative. Well, we can do what we did before, but we could generalize it. We're going to cut our interval from a to b into n little sub-intervals, but we're going to be as general as we can. So we're going to say the pieces don't have to all be the same size. In each one of these sub-intervals, we're going to choose one point called ck, and that's where we're going to measure the height of the rectangle. The width of each subinterval we're going to call capital delta xk. So that's going to be xk, the right-hand number, minus the left number, minus x to the power x, k minus 1. On each one of these little subintervals, we're going to draw a rectangle of width, delta xk, and height f of ck. So, for example, the kth rectangle has width delta xk and height f of ck. Now, if our function is negative, we're going to have a rectangle of negative height. If our function is positive, we're going to have a rectangle of positive height. That's okay, that's what we want. So if our function is negative, we're going to have a rectangle with negative area. That's okay. If we add all these areas together, the sum from 1 to n of height of the rectangle, f of ck, multiplied by the width of the rectangle, delta xk, then we get something called a Riemann sum for f on the closed interval from a to b. And then we want to take the limit as n tends to infinity, or if I'm being careful, if I'm being more precise, actually we want to take the limit as the biggest interval width goes to 0. Sometimes this limit exists and sometimes this limit does not exist. If this limit does exist, then we have a name for it. We call it the definite integral of f over the closed interval from a to b. And we write it like this, if the limit exists. So if the limit of the Riemann sums exists, we can write the value of the limit like this. Again, this stretched letter s is called the integral sign. The function that we're considering is called the integrand, and the dx on the end tells us that x is the variable of integration. Two more things here. We have numbers a and b, which tells us which interval we're dealing with. The a at the bottom is called the lower limit of integration, and the b at the top of the integral sign is called the upper limit of integration. And we read this as the integral of f from a to b. And what does this mean? This means the area between the graph of a function and the x-axis for x between a and b. Using the idea that if we're above the x-axis, if f is a positive function, then we have positive area. If we're below the x-axis, or if f is a negative function, then we have negative area. If the definite integral of f from a to b exists, then we say that f is integrable on the closed interval from a to b. For example, we've looked at the function 1 minus x squared on the interval from 0 to 1. We wrote down a Riemann sum, we calculated its limit, and we found the number. Because the limit of the Riemann sums exist, this function is integrable on this interval, and its value is equal to the limit of the Riemann sums. Its value is equal to 2/3. Let me just remark that it doesn't matter which letter we use here. The integral of f of x dx from a to b is the same as the integral of f of u du from a to b, and that's the same as the integral of f of t dt from a to b. It doesn't matter if we use x or u or t or any other letter here. This is called a dummy variable. Theorem. If f is continuous on a closed interval, then f is integrable on that interval. If f has finitely many jump discontinuities but is otherwise continuous, then f is integrable on this interval. What do I mean here? Well, let me draw a quick graph. Let's suppose our function has a continuous bit, and then it jumps to another number, and then another continuous bit, jumps to another number, and then another continuous bit, and so on. As long as it has finitely many pieces, and on each one of these pieces it's continuous, and as long as the left or right hand limit at each one of these end of these pieces exists, then f is integrable on the interval from a to b. Not all functions are integrable. Remember, integral means the limit of the Riemann sums exists. And I'm saying this function is not integrable on the closed interval from 0 to 1. I have a function which is equal to 1 if x is a rational number, and the function is equal to 0 if x is an irrational number. Why is that? Well, remember, when we're writing down a Riemann sum, we can choose where we measure the height of each rectangle. So, for example, if we choose to measure the height at a rational number, then our rectangles will all have height 1, like this. And then when we add them together, we'll get 1, and then the limit of 1 is 1. But we don't have to do that. If we wanted to, we could choose to measure the height of each rectangle at an irrational number. But then every rectangle would have height 0. 0 plus 0 plus 0 plus 0 is 0, and then take the limit of 0, you get 0. So some Riemann sums would be equal to 1, and some Riemann sums would be equal to 0, and some Riemann sums would be equal to some number between 1 and 0. There doesn't exist a common limit of all of the Riemann sums, so that means the function is not integrable. The previous theorem said if f is continuous, then f is integral. That means if f is continuous, then all of the Riemann sums that we could possibly write down would all have the same limit. Theorems. Let's suppose we've got two functions which are integral, and let's suppose we've got a number called k. I want to run through some properties of definite integrals. First one is more of a definition than a theorem. We can swap the limits of integration. Instead of a on the top and b on the bottom, we can swap them around to have b on the top and a on the bottom, as long as we add a minus sign in the front. Property number 2. The integral of kf is k multiplied by the integral of f. In other words, anytime we have a number inside an integral, we can take it outside of the integral. The integral from a to c plus the integral from c to b is equal to the integral from a to b. Well, that should be clear from the picture. The integral from a to c is this blue area. The integral from c to b is this pink area. And the integral from a to b is all of this area. And what this result is saying is blue plus pink is equal to orange. And that should be clear from the picture. The integral from a to a of f of x dx is equal to 0. Again, look at the picture. What is the area of this vertical line? Lines have area 0. The integral of f plus g is equal to the integral of f plus the integral of g. That's just the sum rule for definite integrals. B minus a minimum of f is less than or equal to the integral of f from a to b is less than or equal to b minus a maximum of f. Okay, so integral of f from a to b is this blue area, and it's all of this blue area. And this theorem is saying the blue area is bigger than the green area. Well, yes, we can see that from the picture. The orange area, that's all of this area, height maximum of f and width b minus a. The theorem says this orange area is bigger than the blue area. And again, we can see that from the picture. Let's suppose that of our two functions f and g, g is always bigger than f on our interval from a to b. It doesn't matter what happens over on the left, doesn't matter what happens over on the right, we're only interested in what happens between a and b. If g is always bigger than f between a and b, then the integral of f must be less than or equal to the integral of g. Yeah, straightforward. We can see that in the picture. Pink area is bigger than blue area. I'm happy with that. A similar idea, if g is greater than or equal to 0 on our interval, then the integral of g from a to b must be greater than or equal to 0. This is a similar idea to the previous one. If f is an odd function means the left side is a mirror image of the right side, then an integral from minus a to a, I colour that in, the integral from minus a to a, so that's all of this, is equal to 2 times the pink area. Yeah, that makes sense to me. If f is an odd function, then the integral from minus a to a of f is 0. An odd function is a function where we can rotate it by 180 degrees and get exactly the same graph. But if we can do that, then that means that then if we have an odd function, that means every time we have a positive area, we'll also have a negative area. And positive plus negative is equal to 0. Again, positive here plus negative is equal to 0. So for example, let's suppose we've got two functions f and h, and we're told that the integral from minus 1 to 1 of f is 5. The integral from 1 to 4 of f is minus 2, and the integral from minus 1 to 1 of h is 7. Then what can we say? Well, first rule was we can swap the upper and lower limits of integration. The integral from 4 to 1 is minus the integral from 1 to 4. So we do minus 2, which is plus 2. Second one, integral from minus 1 to 1 of 2f plus 3h. We can use the sum rule and the constant multiple rule to write this as 2 times the integral of f plus 3 times the integral of h. We know that the integral of f is 5, and we know that the integral of h is 7, so we're doing 2 times 5 plus 3 times 7. And then finally, the integral from minus 1 to 4, we can split this up into two sub-intervals, the interval from minus 1 to 1 and the interval from 1 to 4. And we know these. The interval from minus 1 to 1 is 5, the integral from 1 to 4 is minus 2. 5 plus minus 2 is equal to 3. Show that the integral from 0 to 1 of the square root of 1 plus cos x is less than or equal to the square root of 2. Well, What are the biggest and smallest numbers of cos? The smallest that cos can be is -1, and the biggest that cos can be is 1. So the biggest that the square root of 1 plus cos x can be is square root of 1 plus 1, or square root of 2. Let me say that again. Because cos is always between -1 and 1, the biggest that this function, this integrand, could possibly be is the square root of 2. The theorem said a definite integral is always less than or equal to the width of the interval, so that's 1 minus 0, multiplied by the maximum value of the integrand. So that's just 1 multiplied by root 2, and we've done this question. Calculate the integral from -2 to 2 of x cubed plus x dx. This is easy because we have an odd function. 3 is an odd number, so x to the power 3 is an odd function. 1 is an odd number, so x to the power 1 is an odd function. Odd function plus odd function is an odd function. The integral from -2 to 2, and the key point is these numbers are the same, 2 and 2. The integral from -2 to 2 of an odd function is always equal to 0. Calculate the integral from -1 to 1 of 1 minus x squared dx. This time our integrand is an even function. The rule for an even function is we can just integrate over half of our domain and then multiply it by 2. Instead of integrating from -1 to 1, we could just integrate from 0 to 1 and then multiply it by 2. But we've already calculated that. We know that the integral from 0 to 1 of this function is 2/3. So we're just going to take 2/3 and double it to get 4/3. Calculate the integral from 0 to b of x dx for b greater than or equal to 0. I'm going to solve this problem 2 different ways. Solution 1, I'm going to use a Riemann sum. Because our integrand is a continuous function, we had a theorem which says that it's integral. That means all of the Riemann sums have the same limit. So we could write down any Riemann sum that we want. And what I want to do is I want to cut my interval from 0 to b into n pieces which are exactly the same width. The width of each one of these pieces is going to be b over n. And I'm going to use the right-hand edge of each interval, that's ck is kb over n, to decide the height of the rectangle. So we're doing this. The top right-hand corner of each rectangle is on the line y equal to x, and we have n rectangles. Okay, so we know that the width of each rectangle is b over n, and we know that the height of the kth rectangle is kb over n. So what we have is b squared over n squared, and then sum of the first n natural numbers. Well, we know the sum of the first n natural numbers. We did this near the start of the course. Week 2, I think, n plus 1 over 2. Or we could write that as b squared over 2, 1 plus 1 over n. To calculate our definite integral, we need to take the limit of this function as n tends to infinity. Well, what happens if we replace n by infinity here? 1 divided by infinity is 0. So it's 1 plus 0 is 1. That means that the definite integral is equal to b squared over 2. Now let's solve this a different way. We've been trying to find the area of this pink rectangle, but this is just a triangle. We know how to calculate the area of a triangle. The area of a triangle is a half multiplied by the height multiplied by the base. Height of this triangle is b, and the base width of this triangle is b. It's just a half multiplied by b multiplied by b, or b squared over 2. Exactly the same answer that we got when we were using limits of Riemann sums. And then we can do this. We can do the integral between a and b of x dx by splitting this up into two integrals. Instead of going all of the way from a to b, we can go from a to 0 and then from 0 to b. Remember, anytime we want to, we can swap the limits of integration. Instead of a on the bottom and 0 on the top, we can swap them around, put 0 on the bottom and a on the top, as long as we add a minus sign. But then we know that the integral from 0 to b is b squared over 2, and for the same reason, the integral from 0 to a must be a squared over 2. So we get our answer, b squared over 2 minus a squared over 2. And that is all I want to talk about in this lecture. In lecture 12, we cover the topics, the fundamental theorem of calculus, the substitution method, and area between curves. Are there any questions?